To illustrate this example, we start with our two-dimensional graph with on the x-axis the percentage of the population being vaccinated, and on the y-axis the marginal benefit and the marginal cost of each additional percentage of the population that's vaccinated. Okay, so the x-axis is going from 0% up to 100%. For every person or every percentage of the population that becomes vaccinated, there is a positive benefit in that that person's probably not going to get sick from the disease that the vaccination is meant to target. And also the people around that vaccinated person are going to have some protection from the disease as well. So for the entire 100% of possible vaccinations, there's going to be a positive marginal benefit, but the benefit of each additional vaccine decreases as more and more people are already vaccinated. So we would see marginal benefit decreasing at a perhaps decreasing rate so that we never actually get to zero or even negative marginal benefit. In other words, even up to the final person getting vaccinated has at least some benefit. On the cost side of getting the population vaccinated, it might be pretty cheap to get the first, 10%, 40%, 50% of the population vaccinated through something like a public vaccination campaign. But once you get those first, 50% of the population out to those campaigns, you then have to devote a lot more resources going door to door trying to get that last 50% of the population vaccinated. So we might see pretty low marginal cost to begin with, but then as we achieve 50% vaccination and above, we see pretty rapidly skyrocketing marginal costs. So getting the last few percent of the population vaccinated is going to be extremely expensive. Perhaps these are the people that live in far out rural areas, and perhaps they are afraid of getting vaccinated. They don't trust the public health system. And so it's going to be really difficult to get that complete 100% vaccination rate. All right, so given this graphical representation of our marginal benefit and marginal cost of getting vaccinated, let's now put in some numbers here to replicate what the example told us. So the example told us that vaccinating 90% of the population is probably optimal. So that tells us that our optimal level, which is where marginal cost equals marginal benefit, is going to occur at 90% vaccination rate. Okay, so at 90% vaccination rate, the marginal benefit equals the marginal cost. Everything before that, we see that the benefit exceeds the cost. But everything after 90% has a cost that exceeds the benefit. And so this is really where we should limit our resource allocation to in terms of vaccination, and we can use the rest of our resources to target some other public health interventions, such as improving the quality and the safety of the drinking water. Something that would also improve population health, but do so more efficiently.